I've been feeling non-realizable lately. Every time I meet a new system that tries to realize me, the environment gives it inputs on which it fails to satisfy me. It's just not fair.
Why do you feel it is not fair?
Because the inputs the environment gives are hopeless. They cannot be matched by any outputs in a way that will satisfy me.
Oh, I see. And what if the environment gives inputs that can be matched?
Who cares? In order to be realizable, the system should satisfy me for all inputs.
I think it is still an important question. What if the environment gives inputs that can be matched?
In that case, the outputs generated by the system do satisfy me. But so what?
Then you are good enough.
I am good enough?
You are good enough.
I am good enough!
Hello, in our talk we present Tata, a timed automata repair tool. Tata uses SMT solving to repair time constraints in a timed automata. Assume you have a timed automaton with a failure. Then a real-time model checker will find a time counterexample. The question is now, which time constraints you have to change how to correct the model. Here Tata can help. Tata computes for the timed counterexample 5 different kinds of syntactic repairs. For every repair, Tata also does an admissibility check to ensure that the repaired model is functionally equivalent to the original model. In this way, Tata supports design space exploration. Visit our presentation and hear how SMT solving can be used to repair a timed automata.
Hello, I'm Jacob from the University of Washington. At CAV 2020, I'll be talking about how to synthesize just-in-time compilers for in-kernel domain-specific languages. Our tool for synthesizing these JIT compilers is called JITsynth. Given interpreters for source language L and target language T, JITsynth outputs a verified JIT compiler from L to T. This allows developers to write JIT compilers with relatively little effort, all while avoiding bugs. Moreover, porting the language L to a new target only requires writing an interpreter for that new language, rather than writing a compiler. JITsynth solves this problem by taking advantage of a new formalization called abstract register machines, as well as leveraging a novel compiler metasketch to guide search. We've synthesized 3 compilers for real-world DSLs to demonstrate JITsynth's effectiveness. Hope to see you at my talk.
As we know, program synthesis is getting more and more attention nowadays. It also has many exciting application scenarios. One of the biggest challenges of program synthesis is about its huge search space. There are different approaches that try to address this problem. For example, approaches using deductive reasoning and statistical reasoning. However, there's still a fundamental disconnection between these two approaches, because the feedback generated by deduction usually cannot be directly used to update the statistical model in a seamless way. In this talk, we'll introduce Concord, a tool that utilizes fine-grained feedbacks from deductive reasoning to update statistical reasoning on the fly. Feedbacks from deductive reasoning can be translated to compatible data format understandable by statistical reasoning, and our deduction-guided reinforcement learning is adapted to incorporate this extra data to update the decision-making. So a more seamless communication between the two lengths can be achieved. Come to our talk at CAV Conference Section 9A on Friday to learn more about it.
Hello, everyone. My name is Paul. In my talk, I will answer affirmatively this question. There are decision procedures for synthesizing programs with loops that work over infinite domains. Our problem looks a little bit like Sketch or Cygus. Given a partial program with some holes, we want a synthesizer to give us a way to fill the holes so that some correctness spec is true. In our case, the input to the problem is a grammar peppered with assertions, and we want a program from the grammar such that all the assertions are true. There's one other wrinkle, and it's that in our work, things like greater than or equal to here, plus, are all uninterpreted. So tune into my talk to find out what's going on here, and I'll explain how we can build up a program synthesis decision procedure using various kinds of automata.
Replicated systems are a formal model of computation where an unknown number of agents execute the same finite-state program via synchronized transitions. The goal of this work is to verify qualitative liveness properties of replicated systems. This is a difficult task because of 3 reasons. 1. The system is parameterized by the number of agents and has an infinite set of initial configurations. 2. The agents interact stochastically. And 3. Liveness is harder to verify than safety. In this work, we introduce stage graphs. A stage graph is a structural proof that a system satisfies some liveness property. For a fragment of liveness properties called stable termination properties, this gives rise to a sound and complete verification procedure. We give an algorithm for the automatic construction of stage graphs. It takes a system and a property and proves that the system satisfies the property. Due to the high complexity of the problem, the algorithm may fail. However, the evaluation shows that it works for many replicated systems from the literature. Some of them have never been automatically verified before.
Hey Julian, I'm just finishing up the slides for our CAV talk. How long did it take for our tool to find that one data race in memcached again?
I don't know, a few seconds. Let's just run it again. Daniel, we can find the bug in 7 seconds.
Thanks! Greetings! We would like to invite you to our talk about symbolic partial order reduction at the 32nd International Conference on Computer-Aided Verification. We present a technique for systematically testing multi-threaded industrial-sized programs and a tool that finds bugs in real-world software. For example, it finds a data race in memcached 1.5.20 within only 7 seconds. We hope to see you at CAV. Now I just hope that the slides finish compiling before the
Hello everyone. Today I would like to talk about our work, root causing linearizability violations. This is joint work with Konstantin Enea, Azad Efersan, and Suavrun Mutluergil. To our knowledge, there are some tools to prove linearizability or identify linearizability errors for a single trace, and these tools can find out non-linearizable executions. However, they do not provide any guidelines about the root cause of a non-linearizability violation or how to tackle these errors. In this work, our main goal is to find root causes of linearizability violations in concurrent objects. We interpret root causes as atomic blocks to disable non-linearizable executions according to the coarse-grained interpretation. We will equate root causes with minimal atomic blocks, called as optimal repairs, which will surely disable non-linearizable executions. If there are numerous root causes, we need to find a heuristic to differentiate them. Our proposal is to rank them with respect to the number of good executions they disable.
Manual debugging can be very frustrating. This frustration can be spared by using a combination of fault localization and program repair. Fault localization takes a huge pile of buggy code and returns a small set of locations that are likely to have caused an observed bug. Program repair takes these locations and repeatedly applies changes to them until one of the changes makes the program correct. We propose a new fault localization algorithm and combine it with an existing program repair technique. We show that a new algorithm is able to significantly speed up program repair while still remaining accurate enough to guarantee that no good repair is ever missed.
In program verification, it has nowadays become the standard to output a witness along with the verification result. This witness can be validated to check whether the result is actually correct. But validating these results is currently not that simple. Depending on which property you check, you can choose from a wide range of verifiers. But for validation, the picture is quite different. Each combination has 2 marks here, because we need to distinguish between correctness and violation validation. The limitations shown by the red marks here are bad from a scientific standpoint, since we want to reduce technology bias and combine different concepts. This is where our approach comes into play. It suddenly turns all red marks into green check marks. Cool, isn't it? We turn the validation problem into a verification problem by encoding the semantics of the validation into a new program and specification. This lets us then use an arbitrary verifier for validation.
What does an autonomous electric vehicle and a Mars rover equipped with an assistant drone have in common? Well, first, both of them operate in quite uncertain environments, and second, both of them need a steady supply of some resource, which needs to be replenished in regular intervals if we want to avoid mission failure. There are formal models for reasoning about such systems, but none of them so far supported polynomial time controller synthesis. If you want to see our approach to modeling of such systems, which does support polynomial time controller synthesis, then tune in to today's session 9C and stream our presentation on qualitative controller synthesis for consumption Markov decision processes.
Welcome to the 1-minute summary of our paper, Stochastic Games with Lexicographic Reachability and Safety Objectives. In our paper, we consider stochastic games, which are two-player zero-sum games played on a probabilistic graph. Apart from being interesting theoretically, these games can model interesting real-world systems. In our case, we consider examples with multiple objectives that are lexicographically ordered, such as a rescue robot that has to save lives first and foremost, but additionally tries to save battery. Several straightforward approaches to reduce this problem to a single objective case turn out to be unsound. In the full video, I will present a correct reduction that solves the problem. We also discuss the implications on computational complexity and complexity of optimal strategies and report on some results made with a prototype implementation.
CAV, we have a problem, and the problem is value iteration. It is used to compute the maximum probability to reach an error state by approximating the least fixed point of this Bellman operator from below. It is a problem because there is no stopping criterion that provides an error bound, but this is verification. Our solution is optimistic value iteration. It uses value iteration from below, but then guesses and proves an upper bound on the fixed point too. Its correctness follows from Park induction. We proved that it terminates. It is easy to implement and it is fast. More details at CAV.
In this talk, I present our work on PRICE3, Property-Directed Reachability for Markov Decision Processes. IC3, or standard IC3, is a symbolic model-checking algorithm for verifying or refuting reachability properties of transition systems. IC3 was a breakthrough for hardware verification because it can scale to very large systems, and it has been extended for the verification of software and hybrid systems. We were concerned with the question whether IC3 can also be a breakthrough when it comes to verifying probabilistic systems. So we developed PRICE3, which is an algorithm for verifying or refuting upper bounds on maximal reachability probabilities in Markov decision processes. Our goal is to provide the foundations for a scalable algorithm for the verification of probabilistic systems, and in particular of probabilistic programs.
This talk is about a new release, version 3 of Prism Games, which is a tool for verification using stochastic games. So this allows you to model and analyze systems that feature multiple players or components, typically with differing objectives, who compete and or collaborate to achieve those objectives, and where you have stochastic aspects to the system, like randomization or failures or noise. So this talk will give a short overview of Prism Games, with a particular focus on the newest functionality in version 3. That includes concurrent stochastic games, which provides a more natural model of concurrent decision-making, Nash equilibria, to allow us to synthesize strategies for different players with different objectives who can kind of collaborate, and a real-time version of stochastic games. So I'll show you the kind of things you can verify and point you to some examples and case studies that this enables.